All right, so number 11 on page 296 says, an archery bow has an effective spring constant of 485 newtons per meter. So that's my K, 485 newtons per meter. The archer draws the bow a distance of 45 centimeters. If the arrow has a mass of 0.03 kilograms, 0.03 kilograms, with what speed, what will be its speed the moment it leaves the bow? Okay, so like here's the bow, and when the string's not drawn back, it would be here. But then the archer's going to draw it back to this spot. So the arrow is sitting here, like this, right? And it says in the question, the archer draws the bow a distance of 45 centimeters. So the X initial is 45 centimeters. And the V initial is 0 because he's holding it. When he releases it, this part that's drawn back is going to come in, and it's going to end up being at the equilibrium spot. So the X final will be 0, right? It'll be back to its rest position. And that's when the arrow leaves the bow, and it's looking for what's the V final there. So going to our energy equation, 1/2 mv initial squared, mgh initial, 1/2 kx initial squared is equal to 1/2 mv final squared, mgh final, 1/2 kx final squared plus E lost. Still no E lost. So initially, it doesn't have a speed. He's holding it. Doesn't have a height, but it has an X, 45 centimeters, which we'll have to change to meters. Finally, has a speed, still no height, and no X at that spot because the arrow gets released when the bow is no longer stretched. So we end up having 1/2 k x initial squared equals 1/2 mv final squared. Again, the halves will cancel, and you're looking for v final, so divide by m. So v final squared is equal to kx initial squared divided by m. The k, we were told, was 485 newtons per meter. The x initial was 45 centimeters, or 0.45 meters squared, divided by the mass, 0.03 of a kilogram. And again, this will be v initial squared. You will have to take the square root. This is a huge number. 3,273.75 meter squared per second squared before you take the square root. And when you take the square root, you get 57.217 meters per second, which is very fast. It's like 200 kilometers per hour or something. Moral of the story, don't stand in front of this arrow. All right, that's number 11. Number 12. A 0.25 kilogram mass is on a frictionless surface, so still no friction. And it's attached to a horizontal spring having a spring constant of 124 newtons per meter. So this time the mass is attached to it. So before you do anything, the x here will be 0. And so, and the k, they told us, was 124 newtons per meter, and the mass 0.025 kilograms. The spring is stretched an amplitude of 9 centimeters. So remember I had said to you in an earlier video that when they say an amplitude, they're just saying how much it's stretched. I'm going to call this my I, 9 centimeters, and I'll make this my F. So out here, when you stretch it, it doesn't have a speed. I'm holding it here. I haven't let it go yet. And when it gets to this spot, it will have a speed which will be its maximum. Okay, and the question asks, what will be the maximum speed? So we're looking for the maximum speed, which is the VF. So 1/2 mv initial squared, mg h initial, 1/2 kx initial squared equals 1/2 mv final squared, mg h final, 1/2 out of space, 1/2 kx final squared plus E lost. All right, no E lost. It said frictionless. I'll probably call this my initial, this my final. So initially, no speed, no height, but it has an x. Finally, a speed, no height, no x, no E lost. So we're left with 1/2 kx initial squared equals 1/2 mv final squared. Again, the halves cancel, and I'm looking for the v. So vf squared equals kx initial squared over m. K, they told us, was 124 newtons per meter. X was 9 centimeters, or 0.09 of a meter squared. And the m was 0.025 kilograms. Again, this is going to be VF squared, and you're going to need to take the square root, and when you do, you get, already square rooted, 6.338 meters per second. Before the square root, 40.176. Okay, that's part A. There is a part B that says, what's the speed of the mass 3 centimeters on either side? So, what did I do with my colored pen? So at a point in here, x equals 3 centimeters, it wants to know what's the speed. So we'll make this our new final. Okay? And we'll do energy again. So 1/2 mv initial squared, mg h initial, 1/2 kx initial squared is equal to 1/2 mv final squared, mg h final, 1/2 kx final squared plus E lost. Now usually at this point people are saying, why can't I just go back and use this? You can't go back and use this part because at this spot, x equals 3 centimeters, it has both an x and a speed. Right? So if I call my initial still out where it was, there's no speed, there's no mgh, but there is a 1/2 kx squared. But this is my new final, and it has both a speed, no height, and a k. So these two terms both stay. So 1/2 kx initial squared equals 1/2 mv final squared plus 1/2 kx final squared. That's why you can't use the same thing as part A. The halves cancel, and we're looking for v final, so it'll be kx initial squared minus kx final squared divided by m. That'll be my v final squared. Put an equal sign in there. So k, 124 newtons per meter. X initial was 9 centimeters, 0.9 meters, minus 124 newtons per meter, 0.03 meters squared, don't forget your squares, over 0.025 meters per, kilograms. We're solving for meters per second. And you will get a VF squared before the square root of 35.712 meters squared per second squared, after the square root 5.98 meters per second. Answer in the back of the book is wrong for this one too, if you were looking. Okay, so hopefully springs are pretty good now. It must be time to introduce friction.